So, hello everyone, thank you for coming for the second graduate student seminar series. So we have another one planned in November, and that is the last one of this semester, but we have another series planned in the spring semester which starts in January. So I hope you will all be there as well. So we have another couple of interesting talks, and the first one is by Soheil Soghrati, and he did his master's at the Isfahan University of Technology in Iran, and there he worked on solid and fluid mechanics problems in complex geometries. And today we'll be talking about computational modeling and design of actively cooled 3D woven microvascular composites. So the floor is yours.
Thank you very much. Thank you, and good afternoon. So today I'm talking about the computational tools and also modeling of 3D woven microvascular composite and active cooling in these materials. The motivation for the work comes from design of advanced materials for hypersonic aircraft. The problem that we deal with in this type of structures is called aerodynamic heating, which causes very high temperature in the airplane due to flight condition. Problems such as radiation, friction, and shock waves can increase the temperature of the airplane and can also be in space shuttle to larger than 1000 degrees Celsius easily. So that's why there's a broad area of research on developing thermal protection systems for this type of structures. More conventionally, there were heat tiles, for example, that are used in space shuttles. Something that you can see here, a close-up here, and they can withstand up to 1500 degrees Celsius, although they are quite heavy. More advanced materials like ceramic woven composite, they can withstand larger temperatures, up to 3000 degrees Celsius. And this project, the goal is to design an autonomic hybrid material that can withstand possibly up to 5000 degrees Celsius. So here's a schematic of the hybrid material that we intend to design. The outer layer is oxide ceramic, which is a thermal and environmental barrier coating. In the middle, we have a functionally graded ceramic metal composite, which withstand damping. And finally, there is the main structural component of this structure, which is a 3D woven composite. It withstands damage, and the goal is to design it from polymer matrix compound. Again, our problem is that polymers are usually degrading at temperatures between 250 to 300 degrees C. And as I mentioned, we expect temperatures as high as 5000 degrees Celsius here. So the way that we try to resolve this problem is by active cooling, meaning that circulating a coolant inside the material to reduce its temperature. Very briefly on the manufacturing of this type of composites, it is done through a method that developed at Autonomic Material System Group, AMS Group at Bateman. It's called the sacrificial fiber technique. They are weaving a special type of fibers, they are called lactide or PLA fibers, in the composite preform, and then evacuate that to form these nice to form microchannels. And here you can actually see that yellow fluid is passing through those microchannels. The diameter can be between 100 to 500 micrometers, and here's the micro CD of those microchannels that are formed through this technique. On the modeling side and simulations, that is the main focus of my project, we are trying to evaluate the thermal response of this material. Here is a schematic of the microvascular composite with so many microchannels in that, and you can see a fluid that is circulating through these microchannels. We can take advantage of symmetry in this material and pick our computational domain and mainly focus on one single microchannel for the numerical simulations. And here we can see the design parameters that we have in this problem. So one of the main challenges is that we have so many parameters that we need to consider in our design. We don't know what is the exact configuration of the microchannel, what is the optimal configuration. For example, if you're using sinusoidal shape, what is the amplitude or wavelength, what is the total length of this specimen, how much flow rate you are passing, and even what type of coolant is the best choice for active cooling. So we deal with so many parameters for design. On the other hand, the objective function and constraints of the design are quite challenging. We need to minimize the void volume fraction of the composite, because when you're designing this microchannel, you're removing part of the material and you're causing damage. So the lowest amount of void volume fraction you have, the better for the structural purposes. Also, we need to minimize the pressure drop in the microchannel, because that directly translates to how much energy you need to provide for active cooling. and you want to minimize it as well. And finally, and the most important objective function is to minimize the maximum temperature. Here in this table, you can see, based on different values of thermal load, what is the temperature in the absence of active cooling. And as I mentioned, for this type of thermal load that we expect to see at Mach number between 5 to 7, the temperature can easily go to 5,000 degrees Celsius. And the constraint we have for the design is to minimize the maximum temperature of, is to maintain the maximum temperature of the coolant, in this case, for example, water, less than a certain value. For example, for water, we don't want to let the temperature exceed 100 degrees Celsius. Now, for computer simulation, we have different choices. Conventional methods like finite element or finite volume method are usually used. So there are three main steps in any of these methods that you choose for a design that you have to do. First, in the computer, we have to create the problem geometry. We have to describe that, for example, we have a sinusoidal shaped microchannel. What is the geometry of the domain? Then we have to create the physical model because we want to simulate a physical phenomena. For example, in the finite element method, we have to create an appropriate finite element mesh for design of the system, as you can see here. And finally, we have to, of course, pass it to a numerical solver to evaluate the thermal response. So now imagine that we want to design this material, and we have to run several different cases, more than 100 cases, with this step. So each time the user has to repeat all these three steps. And actually, the main challenge falls in the second step, because the quality of this physical model translates to the quality of the final simulation and the accuracy of the result. And again, as I mentioned, it's, if I don't say impossible, it's very difficult to do this 100, 200, or 1,000 times for design of such complex problem. That was the motivation for me to develop a method that is called interface and read generalized finite element method. I'm not going through the formulation. If you have any question, I would be happy to answer afterwards. But the main goal of this method is basically to eliminate the first two steps of the design process, meaning that the user don't have to create the geometry or the physical model. Everything is taken care of in the code that you are using for solving. In other words, you are removing the complexity from the user and embed that in the code that you are using for design. So a lot of computational geometry, of course, involves in creating these geometries through the code. And then when you are eliminating those two steps, it's also very important that you have to maintain the accuracy. So this method should still work as accurate as those conventional methods. These are the two things that we achieve with the IGFM solver. Here you can see schematic of the computational geometry involved in creating these geometry. Different steps are listed here to recognize geometry, doing some tutorialization for recognizing the surfaces, and then finally creating nicely formed and smooth surface. So the main goal, as I mentioned, was to simulate actively cooled material. Here you can see the geometries created through that, nicely formed microchannels, and then the thermal response evaluated through this method. And as we tested the method, it was just as accurate as those conventional methods. And when I was developing IGFM, I was also thinking that this method can have many other applications. So I tried to develop a virtual microstructure modeling library in that can be applied to different types of material microstructures. For example, here you can see the application for simulating a granular composite and the thermal response of that. The method can be applied to even more complex problems. For example, a unit cell of 3D woven composite that we deal with here can also be modeled with the IGFM. And again, the user doesn't have to create these geometries through a software. Everything is taken care of in the code by passing some analytical function to the code. And again, the thermal response. For example, here you can see slices of those, the temperature field, and you can see what happens in the middle. The code can accurately capture the impact of these fibers, their impact on the thermals. So now we have this solver that we could do everything in an autonomic fashion, meaning that running hundreds and hundreds of different cases without the user having to do anything, just by changing the geometry to the code. And that's how we ran several different cases. And here I have listed the Q result that we had for the microvascular system. Here, for example, you can see the temperature field for different configurations of the microchannel run through the code. So first of all, we mentioned that quite to our surprise, when we are going to flow rates larger than a certain amount, in this case 0.5 liter per minute, the straight microchannels were actually the optimal configuration. We also mentioned that for design of the system, the amount of coolant that we need to provide is actually dictated by what is the maximum allowable temperature of the coolant and not that of the composite. So for example, this is the design diagram that we obtained for design of the system. It shows based on how much heat flux applied to the system, and it shows the maximum temperature. I don't know if that is completed here, but it shows the maximum temperature in the composite and also the maximum temperature of the coolant. The contour line is the maximum temperature of the composite, and the dashed lines are the maximum temperature of the coolant. And then we can, based on that, determine that how much flow rate we need to provide for each case. So for example, this shows that for the solid part, which is the composite, we need to provide a flow rate of 1.3 millimeter per minute, which is not that high. But then you actually have to multiply it almost by 3 times to satisfy the constraints on the maximum temperature of the fluid. So again, the other conclusion was that maybe we have to look at other type of coolant. So when we started this project, we said, okay, we look at water, then we look at better coolants like polyalpha olefin that is commonly used in aerospace industry. And again, it was quite surprising to see that water is actually a far better coolant compared to those coolants, especially because this is a composite material. We don't deal with corrosion here, so we can implement water for cooling. So the conclusions of the work, a mesh-independent technique, the IGFM was developed for simulating several different types of problems. It was applied successfully for the design of actively cooled microvascular materials. And the numerical solutions showed the feasibility and also efficiency of active cooling for the possibility of using this material for thermal protection system in hypersonic aircraft. There are several things, especially on the numerical part of the project, that we want to develop. For example, we want to develop more sophisticated optimization scheme. Right now we ran several different cases, but there are actually more sophisticated optimization schemes. Methods like sensitivity analysis and gradient-based optimization techniques we want to develop. We also want to create more realistic geometric models using X-ray tomography. So converting an X-ray tomography to an IGFM model directly is the next step that we're working on that, and also more sophisticated damage model, because everything I showed you was the thermal analysis. Now we want to move to the structural part. So we have actually used IGFM before for developing damage model in, for example, granular composite. The red part shows as you are cooling this specimen how much damage is caused here, but we want to also use damage model for composite material in the code. So it comes to the end of my talk. Just acknowledgement from my advisor, Professor Kubal, our collaborators in the project, Professor Soros, Wyatt, and Duarte, and everybody in Professor Kubal's group and AIM's group that I have collaborated. Thank you.
Well, thank you. Do we have any questions from the audience? Come on, a couple of minutes. No one? Well, it's always difficult to come up with a question immediately. So you said you studied it without looking at the structure, the influence of all these micro channels, yes, on the structure itself and how rigid it is. Isn't that the really important part of the design?
Oh, the important part of the design, so we actually implemented as one of our objective functions the void volume fraction, because when you are embedding this microchannel, you are removing part of the material. Mm-hmm. So we somehow looked at that in our design process by minimizing that void volume fraction. But the next step, as I mentioned, is to directly simulate the structural behavior. So we want to develop damage model for that, and this is definitely the next step we want to do. Of course. Okay. Well,
other questions from the audience? Yes.
Do you think the methods that you've developed would be useful for instance, looking at biological systems, like the cooling that effects that could arise from blood flow in the brain, for instance?
Yes, so the main advantage of the method, and that is actually what I'm trying to further develop, is to model complicated geometry. So you can model all of those problems with conventional method. The problem is each time you have to create that geometric model. And it is not always easy to have a good quality for that. Even with very sophisticated software, sometimes the geometric model that you create is especially for those systems, for example, when you're from X-ray tomography, or just you want to describe a complicated geometry, it's not very easy to create just a physical model. So the method is supposed to take care of these things automatically. And then, of course, yes, you can develop more or other type of physical systems. For example, example, blood flow. There are different types of equations that describe that problem, but the geometric part is taken care of.
There's time for another question, if someone has a question. No? Well then, let's thank Soheil once again.